Hello, my name is Ben Cranston and I'm here to solve this problem for you today. So let's go ahead and get started and I'll give a quick description of the problem. So we start out with a capillary, and the capillary is divided into two parts, and one part is completely full of gas A and the other part is completely full of gas B. Now what we're going to do is remove this middle divider and let the gases mix completely and uniformly. Now, you'll note this whole time there's a uniform pressure and temperature within the whole unit. So the pressure and temperature is constant throughout this whole process. Now, with that situation in mind, we are tasked to go ahead and try and figure out the relationship between molar diffusion flux and mass diffusion flux. Well, in order to discuss that, we should probably first talk about the relationship between molar flux and mass flux without the diffusion element. So let's go ahead and get into that. So I'll start out with this blue marker right here, and let's talk about the total molar flux, the total molar flux. That would be represented by N. That, of course, equals the sum of Na plus Nb. Okay. That would be the flux of A plus the molar flux of A plus the molar flux of B. That's, pretty simple definition of what a sum is. Now, this is actually going to be equal to 0. Because there is a uniform mixing, for every 1 mole of B that goes over the right, 1 mole of A goes over the left. And because of that, we can know that the total molar flux, which is the exchange of moles between the two sides, the total molar flux is going to be 0. So with that in mind, and this is going to become important to solve this problem, let's go ahead and kind of create another definition for what we're going to try to do. We are going to go ahead and define how the molar flux of component A relates to the mass flux of component A. So this is something that, if we think about it for a second, we know that flux is a quantity over area times time. So quantity on top, area and time on the bottom. Well, the quantity in molar flux is moles, the quantity in mass flux is mass. So to relate those two, we just need to know the relationship between mass and moles. That's pretty easy, that's the molecular weight. So yeah, that's how you relate mass flux to mole flux. Now, a lot of everyone is thinking, well, can't we go ahead and just say that Ja, or the mass diffusion flux, equals the molecular weight times molar diffusion flux? Well, that's not really the way it works, sadly. I mean, that would be nice, this problem would be over, but it's not over. That's not the way we solve this. And we can know that from basically just looking at the definitions of mass and molar flux. So let's go ahead and write these out. So the definition of molar flux is that molar flux of a component, and I mean molar flux of a component for now, let me go back a second. The definition of molar diffusive flux for component A is going to be the molar concentration of A times the velocity of component A, and we're going to subtract the average molar velocity of all the components in the system. So it's the definition of molar velocity. Definition of mass velocity is similar, but with mass-related terms. So mass diffusion flux is going to be the mass concentration, or density, I'm going to proceed to call it density, over, or times the velocity of component A, now that's the same velocity of component A you have right here, minus the net mass velocity. So now we have these two things defined. We have to find a way to manipulate these so that they're the same. So that, you know, maybe there's not really an intuitive way to do that immediately looking at this, but I think I can reduce one of these formulas to make it a little bit easier to merge them together. So we know that the total, let's go back right here, the total molar flux is equal to 0. We've already established this. If you don't understand, go back and take a look at that bit. We can also know the total molar flux equals the concentration of the system times the molar average velocity. So if that's 0, the concentration can't be 0. That wouldn't make any sense. That's not really, you know, we have stuff here, the concentration is therefore not 0. So that means that the total the average molar velocity must be 0. Now that's pretty good. I mean, that's something that's pretty important to this problem. So that lets us simplify this a lot. We can set this equal to 0. And if we set that equal to 0, I'm going to go ahead and get out my green marker and shake it up a little bit so that way some of the juice falls back down. We can bring this down, and we can say that the molar diffusion flux equals the concentration, the molar concentration of A times the average velocity of A. Now, a little fun fact here, ça va means how's it going in French. Pretty interesting that I thought it worked out that way. This formula like this doesn't really give us an opportunity to bring anything over here, but we can shift it around a little bit, use the common term, and we can say that the velocity of component A equals the molar velocity, or the molar diffusion flux of A over the concentration of A. Now that's a little bit more helpful. So I'm going to go ahead and put this in here and multiply it out, and I'll write it out and then explain it. So So that's pretty cool, right? Now we've managed to get some kind of a relationship between the between the molar diffusion flux and the mass diffusion flux. But this formula can actually be simplified even more to give us something that's going to be even more helpful to what we're trying to do. So we're going to go through a couple steps to kind of merge some of these concepts and merge some of these values, so that way they can all equal out to the same thing. So this is the mass diffusion flux. I'm going to take that down a step. And then the first merger I'm going to do is the density of A over the concentration of A. So density is mass over volume, right? It makes it hard. That's how everyone remembers it, I think. I don't know for sure. Concentration is, the molar concentration is moles per volume. So if we have mass per volume over moles per volume, that reduces to mass per mole. Mass per mole is, of course, molecular weight. It's like back here. So the molecular weight of A times the molar diffusion flux. Now we're gonna break down this term a little bit more. So this is probably the more difficult and less intuitive thing to break down. So I'm going to go through in a couple steps and break it down. We're going to start out, what is the meaning of mass average velocity? Well, the mass average velocity is a weighted average of the velocities of all the components. In this case, the components are A and B. So let's go ahead and write out what this is equivalent to. This is equivalent to the sorry, my bad, getting a little bit ahead of myself there. The density of component A multiplied by the, oh, there's no one here to answer my question, multiplied by, sorry, I'm blanking for a second, multiplied by the velocity of component A. That, yeah, sorry, I apologize, I blanked for a second. In addition, the same thing for component B, all over the total mass concentration. Now, let's break this down again. This isn't really going to be helpful to plug this in right here. There's going to be a little bit of cancellation, but not much. But there's some more relationships that we can kind of incorporate here, and that should make this a lot easier to kind of break down. So we have already solved for what the average velocity of component A is. It's ça va. Now, if we were to do the same thing for component B, all this math would work out the same. We would just get the average velocity for component B equals the molar, the molar diffusion flux of component B over CB, the concentration of B, or cornerback if we're playing football. But we're not playing football, so we'll just call it the concentration of B. Well, these two concepts can be brought in here, and they can make things a lot more simple. Because if you look at it, here's what we're going to do. We can bring this in, and we're going to have the density of B, or A, I'll just say B for the sake of argument, the density of B over the concentration of B. So density over concentration, we've already worked that one out. Density over concentration is molecular weight. We did that back there when we solved and brought in a molecular weight. So with that in mind, we know the molecular weight of A times the mass diffusion, times the molar diffusion flux of A, plus the same thing for B, all over rho equals the total velocity. So this is getting a little bit closer to something that we can work out, because we're getting close to being able to take out, basically take out this molar diffusion flux, and that would really simplify the formula a lot. So another concept that can be brought in order to kind of justify this shakeup is the relationship between the molar diffusion flux of A and the molar diffusion flux of B. So what's this relationship? How do we relate these two ideas? Does anyone have any ideas? I don't have a class, so I don't have anyone help me out or anything like that. So I will go ahead and try to explain it a little bit more. There is the net molar flux. The net molar flux, not diffusion flux, molar flux is 0. That's because for every mole of B that goes over to the left, a mole of A comes over to the right. And so they cancel out, they're 0. Well, the diffusion flux is going to work the same way. We know that because of the way, we can look at the definition. It's going to work the same way. So the molar diffusion flux of A is going to be the opposite of the molar diffusion flux of B, or molar diffusion flux of A equals negative molar diffusion flux of B. Now that's, sorry, I apologize. That's pretty helpful to what we're trying to go ahead and do here, because now we can pull in another molar diffusion flux of A. We can just take out this molar diffusion flux of B, and that's pretty helpful to what we're trying to do here, right? Because that makes this a whole lot simpler. Now we can get, sorry, I was just thinking about it for a second. now we know that the molar diffusion flux of A times the difference between the molecular weights of A and B over the total density equals the velocity, or the average velocity, the average mass velocity. I apologize. That's kind of helpful here, because that lets us bring in another another term that is that's this term of another molar diffusion flux of A term. So let's go ahead and I'm just going to go ahead and skip down a little bit and start writing blue, because I think blue might show up a little bit better. I'm not certain, but I sure hope it does. And I'm going to go ahead and copy this down once. So I'll explain it once I'm done copying it down. Okay, so this formula is nearly just algebra. There's one last step, one last concept I want to work in here to simplify this even more, so that way we can have a nice, clean relationship between mass diffusion flux and molar diffusion flux. So let's really quickly go over what we have so far. Mass diffusion flux equals molecular weight times molar diffusion flux minus density of A. We got another molar diffusion flux, and then the difference between the molecular weights of A and B, then we got the total density. Well, so what can be further kind of reduced and simplified here? I think the best way to do that would be to look at some units. So let's look at the density of A over the total density. Density is mass over volume. It makes a little heart. Isn't that cute? I think it's cute. Okay. But it's mass of A over the volume total. Now, it's that density over this density. So we've got the mass total over the volume total. Well, these two are going to cancel, right? So that leaves us with the mass of A over the total mass. Well, what is that? That's a great question. I just asked myself. Thank you, self, for asking such a great question. That is going to be mass fraction. Mass of component over mass total. Well, shoot, that simplifies this even more. So now we've got, I'm going to go ahead and pull these molar diffusion fluxes out front, because that'll be, you always want to combine your terms. That's fifth grade level stuff. I mean, we got this under, we can do this. Minus, remember, mass fraction of A. Mass fraction of A times the molecular weight of A minus the molecular weight of B. There, I should add another parentheses just for thoroughness. And yeah, look at that. So this describes the relationship between mass diffusion flux and molar diffusion flux. Mass diffusion flux is molar diffusion flux times the molecular weight of A, and by the way, of course, I mean of component A for both these. This isn't the relationship between those two things total for the system or anything like that, minus the mass fraction of A times the molecular weight, the difference between the molecular weight of A and the molecular weight of B. So this is a pretty useful formula, because if we can figure out one of the fluxes and the mass fraction of the component, so if we can figure out the molecular diffusion flux and the mass fraction, I mean, these are just constants. They're just references from a periodic table, these molecular weights. So that allows us to relate all these concepts. If you know two, you know the other one. I'm just saying that these molecular weights are just something you can read from the periodic table and some addition. So yeah. This is a pretty helpful formula we just derived, and it relates molar diffusion flux to mass diffusion flux. So thanks for watching. I hope you were able to learn something, and yeah, have a nice day. Bye-bye.